Welcome to today's session. In this video, we'll be solving LeetCode problem number 1310, titled XOR queries of a subarray. This problem involves efficiently calculating XOR values for specific subarray ranges based on a list of queries. It's a fascinating problem that combines array manipulation with bitwise operations. Stay tuned as we break it down step by step. In this problem, you are given an array called ARR and a list of queries, where each query specifies a pair of indices, L_i, R_i. The task is to calculate the XOR of all elements in ARR between these indices, inclusive. The result for each query is stored in an output array called answer, where each element corresponds to the XOR result for the respective query. For example, if ARR contains integers and you are provided with a query like 1, 3, it means you need to compute the XOR of all elements from index 1 to index 3 in ARR. The problem guarantees that the input sizes for ARR in queries can go up to 30,000, so efficiency is an important factor to consider. Now, let's explore some specific examples to better understand the input, output, and expected behavior of the solution. In the first example, the input array is 1, 3, 4, 8, and the queries are 0, 1, 1, 2, 0, 3, 3, 3. The output array is 2, 7, 14, 8, and here's why. For the first query, 0, 1, we compute the XOR of elements at indices 0 and 1, 1_3, which equals 2. Next, for the query 1, 2, we calculate the XOR of elements at indices 1 and 2, 3_4, which equals 7. For the third query, 0, 3, we compute the XOR of all elements, 1_3 to the power of 4_8, resulting in 14. Finally, for the query 3, 3, since the start and end indices are the same, the result is simply the value at index 3, which is 8. This example illustrates how XOR operations are applied to different ranges of the array, and the results are stored in the output array. In the second example, the input array is 4, 8, 2, 10, and the queries are 2, 3, 1, 3, 0, 0. The output array is 8, 0, 4. For the first query, 2, 3, the XOR of elements at indices 2 and 3 is 2_10, which equals 8. For the second query, 1, 3, the XOR of elements at indices 1, 2, and 3 is 8_2_10, which equals 0. For the third query, 0, 0, the result is simply the value at index 0, which is 4. Additionally, the problem comes with constraints and edge cases. For example, when the array has only one element and there is a single query, the result is just that element. If a query specifies the entire array, the XOR of all elements is returned. For large inputs, it's crucial to design an efficient solution to handle up to 30,000 queries on arrays of size 30,000 without exceeding time limits. To solve the problem of computing XOR queries on a subarray, we need to evaluate the XOR of elements in a given range, L_i, R_i, for multiple queries. The brute force approach provides a straightforward way to achieve this by directly iterating through the subarray defined by each query. For each query, we initialize the XOR result to 0 and loop through the range, L_i, R_i, computing the XOR of each element in the subarray. Once the XOR is calculated, we append the result to an output array. While this method is simple and follows the problem definition directly, it has significant inefficiencies. Specifically, the time complexity is proportional to the total number of elements being processed, which is O, n*q, where n is the average range length and q is the number of queries. This makes the brute force approach impractical for scenarios involving large arrays or numerous queries. On the positive side, it requires minimal additional space, making it a space-efficient, though computationally expensive, solution. The brute force approach, while simple, has major drawbacks. It recalculates the XOR for overlapping ranges across queries, leading to redundant computations and inefficiency for large input sizes. To address this, we can use an optimized approach called the prefix XOR technique. The key insight behind this method is the property of XOR, a_a equals 0 and a_0 equals a. By leveraging this property, we can preprocess the array into a prefix XOR array, where each element represents the XOR of all elements from the start of the array up to that index. Using this pre-computed data, the XOR for any subarray, L_i, R_i, can be calculated in constant time. Specifically, if L_I 0, the result is prefix R_I, prefix L_I 1. If L_I equals 0, the result is simply prefix R_I. This eliminates the need for redundant calculations within overlapping subarrays. The pre-processing step to compute the prefix XOR array takes linear time, and each query is processed in constant time. As a result, the total time complexity is reduced to O, n plus q, where n is the size of the array and q is the number of queries. The prefix XOR approach offers several advantages. It enables highly efficient query handling, with each query processed in constant time. By leveraging pre-computed data, it removes redundancy and ensures that overlapping subarrays across queries do not result in wasted computation. This makes it an ideal solution for scenarios involving large datasets or numerous queries. The main trade-off is the additional memory required to store the prefix XOR array, which increases the space complexity to O, n. However, this is a reasonable cost given the significant time savings. The combination of reduced query time and the elimination of redundant calculations makes the prefix XOR approach highly scalable and efficient. The critical insight driving this strategy is the XOR property, allowing us to compute subarray results using previously computed values. This pre-processing step transforms the problem into a more manageable form, enabling rapid query resolution without sacrificing correctness. When comparing the brute force and prefix XOR approaches, the trade-offs become clear. The brute force method is simple to implement and does not require additional memory. However, it is inefficient for large inputs due to redundant computations, making it unsuitable for scenarios with high constraints. In contrast, the prefix XOR approach is highly efficient, with constant time query handling and scalability for large datasets. The trade-off is the additional memory used for the prefix XOR array, but this cost is justified by the significant performance gains. Given the constraints of the problem, the prefix XOR approach is the superior choice. It ensures both correctness and efficiency, making it the recommended strategy for solving XOR queries of a subarray. By leveraging pre-processing and the properties of XOR, we achieve a solution that balances computational efficiency with manageable memory usage, addressing the limitations of the brute force method effectively. This problem asks us to compute the XOR of elements in a subarray for multiple queries efficiently. Given an array ARR and a list of queries, where each query specifies an inclusive range, L_I, R_I, our goal is to calculate the XOR of all elements in the specified range for each query. Instead of directly computing the XOR for every query, which would be inefficient, we use a pre-processing technique called prefix XOR to optimize the process. The idea is to create a prefix array, where each entry stores the cumulative XOR of elements from the beginning of the array up to a certain point. This allows us to calculate the XOR for any subarray in constant time. To set this up, we initialize prefix 0 equals 0 to handle the XOR of an empty range. Then, we iteratively compute the XOR values for the prefix array using the formula prefix I equals prefix I1 ARR I1. This prepares the data structure we need for efficient query processing. Once the prefix XOR array is computed, it becomes straightforward to answer the queries. For a query, L_I, R_I, the XOR of the subarray ARR, L_I, to ARR, R_I, can be calculated as prefix R_I plus 1, prefix L_I. This works because the XOR of a range, L, R, is essentially the XOR of the entire range, 0, R, minus the XOR of the range, 0, L1. If the lower bound L_I is 0, the result simplifies to just prefix R_I plus 1, as there is no range to subtract. After computing the result for each query, we store it in a results array. The key advantage here is that we leverage the properties of XOR, such as its associativity and the identity property x equals 0, to enable constant time range queries. This makes the algorithm highly efficient, with a pre-processing time of O, n, and a query processing time of O, 1, per query. For m queries, the total time complexity is O, n plus m, which is a dramatic improvement over the naive O, m*n approach. These principles ensure that our solution is both fast and scalable. There are a few edge cases to handle in this problem. If the range of a query is invalid or the array itself is empty, we can handle this gracefully by returning 0 or skipping the query altogether. Additionally, if the query range consists of a single element, meaning L_i equals R_i, the result is simply the value of the element at that index in the array, which can be directly retrieved without any computation. To implement this solution, we rely on two key data structures. The first is the prefix array, which efficiently stores cumulative XOR values for fast range queries. The second is the results array, where we store the XOR values for each processed query. Finally, the algorithm is efficient in terms of space as well, requiring O(n) space for the prefix array. This optimization, combined with the time complexity of O(n plus m), makes the approach suitable for large datasets. To illustrate the algorithm, let's walk through an example. Suppose the input array is ARR equals 1, 3, 4, 8, and the queries are 0, 1, 1, 2, 0, 3, 3, 3. First, we compute the prefix XOR array. Starting with prefix 0 equals 0, we calculate each subsequent value. Prefix 1 equals 0 to the power of 1 equals 1, prefix 2 equals 1 cubed equals 2, prefix 3 equals 2 to the power of 4 equals 6, and prefix 4 equals 6 to the power of 8 equals 14. The final prefix array is 0, 1, 2, 6, 14. Now, we use this array to efficiently answer the queries. For the first query, 0, 1, the result is prefix 2, prefix 0 equals 2 to the power of 0 equals 2. 4, 1, 2, its prefix 3, prefix 1 equals 6 to the power of 1 equals 7. 4, 0, 3, the result is prefix 4, prefix 0 equals 14, 0 equals 14. Finally, 4, 3, 3, the result is prefix 4, prefix 3 equals 14, 6 equals 8. The final output is 2, 7, 14, 8. This demonstrates how the prefix XOR technique allows us to efficiently process the queries and achieve the desired results. In this implementation of the XOR queries of a subarray problem, we aim to compute the XOR of elements in a given subarray efficiently. Let's break down the solution step by step. First, we use a pre-processing technique called a prefix XOR array. The prefix XOR at index I represents the XOR of all elements in the ARR array from index 0 to I1. This allows us to compute the XOR of any subarray, L, R, in constant time using the formula, prefix XOR, R plus 1, prefix XOR shell. In the first step, we initialize a prefix XOR array with n plus 1 elements, one extra to handle edge cases. We then iterate through the input array ARR, computing the cumulative XOR at each step and storing it in prefix XOR. Next, we process each query in the queries list. Each query provides the range L, R. Using our prefix XOR array, we compute the XOR for the subarray L, R in constant time and append the result to the result list. Finally, the result list, which contains the XOR values for all queries, is returned as the output. This approach is efficient, with a time complexity of O(n plus q), where n is the size of the array and q is the number of queries. This efficiency is achieved by avoiding redundant computations for overlapping queries, thanks to the prefix XOR array. This is the Java implementation of the LeetCode problem number 1310, XOR queries of a subarray. The solution mirrors the Python logic, using a prefix XOR array to pre-process the input array for efficient query handling. The main differences in Java include explicit type declarations, array initialization, and the use of a 2D array for queries. The XOR queries method computes the prefix XOR array, processes each query, and returns the result as an array of integers. To solve the problem, we begin with the concept of a prefix XOR array. This array helps us efficiently compute the XOR of any subarray in constant time. We initialize the array prefix XOR with zeros, with one extra element at the start to simplify calculations. Here, the input array is 1, 3, 4, 8. As we iterate through the array, each prefix XOR, I plus 1, is calculated as the XOR of the previous prefix value and the current element from the input array. For example, the first value is 0, 1 equals 1, then 1, 3 equals 2, followed by 2, 4 equals 6, and finally 6, 8 equals 14. This gives a prefix XOR array of 0, 1, 2, 6, 14. Once we have this array, we can process each query efficiently. For any query, L, R, the XOR result is given by prefix underscore XOR, R plus 1, caret prefix underscore XOR, L, leveraging the properties of XOR. This allows us to compute results without recalculating the XOR for every subarray from scratch. Now, using the prefix XOR array, let's process the queries for the first example. For the query 0, 1, the result is prefix underscore XOR, 2, caret prefix underscore XOR, 0, which equals 2 caret 0 equals 2. For the second query 1, 2, it's prefix underscore XOR, 3, caret prefix underscore XOR, 1, giving 6 caret 1 equals 7. Finally, 4, 0, 3, the result is prefix underscore XOR, 4, caret prefix underscore XOR, 0, which equals 14 caret 0 equals 14. This means the final results for these queries are 2, 7, 14. Now, let's consider a second example that involves an edge case. Here, the input array is 4, 6, 7, and the queries contain just one entry, 0, 2. We compute the prefix XOR array in the same way. Starting with an initial state of 0, 0, 0, 0, we iterate through the array 0 caret 4 equals 4, for caret 6 equals 2, and 2 caret 7 equals 5, resulting in 0, 4, 2, 5. For the query 0, 2, the result is prefix underscore XOR, 3, caret prefix underscore XOR, 0, or 5 caret 0 equals 5. So the final result for this query is 5. Now let's explore a third example, where the input array is 5, 1, 2, 3, and we have two queries, 0, 1, and 2, 3. To start, we build the prefix XOR array. Beginning with an initial state of 0, 0, 0, 0, 0, we compute 0 caret 5 equals 5, 5 caret 1 equals 4, for caret 2 equals 6, and 6 caret 3 equals 5, giving us the final prefix XOR array of 0, 5, 4, 6, 5. Using this array, we can now process the queries. For the first query, 0, 1, the result is prefix underscore XOR, 2, caret prefix underscore XOR, 0, or 4 caret 0 equals 4. For the second query, 2, 3, the result is prefix underscore XOR, 4, caret prefix underscore XOR, 2, or 5 caret 4 equals 1. This means the results for these queries are 4, 1. By leveraging the prefix XOR array, we efficiently answer each query in constant time, regardless of the size of the subarray. In analyzing the time complexity of our solution, we start with the prefix XOR array construction. Here, we iterate through the input array ARR once, performing a single XOR operation for each element to compute the corresponding value in the prefix underscore XOR array. This process requires n time, where n is the size of the input array. Next, we process the queries. For each query defined by the range L, R, we calculate the XOR of the subarray using two operations, prefix underscore XOR, R plus 1, caret prefix underscore XOR, L. Since each query is resolved in constant time, or O1, processing all M queries takes a total of O(m) time. Combining these two steps, the overall time complexity of the solution is O(n plus m), where n is the length of the array and m is the number of queries. This holds true for the best, average, and worst cases because both steps depend linearly on the input size and the number of queries. Now, turning to the space complexity, the solution uses two main additional data structures, the prefix underscore XOR array and the result array. The prefix underscore XOR array has a length of n plus 1 extra element to store the initial 0 value for easier computation, requiring n space. The result array, which stores the answers to all m queries, requires m space. The input array ARR and the list of queries do not contribute to additional space usage as they are part of the input and are not duplicated or modified. When we combine the space requirements of the prefix underscore XOR and result arrays, the total space complexity of the solution is n plus m. When comparing the optimized approach to the naive approach, the improvements become clear. A naive solution would calculate the XOR for each query by iterating over the subarray ARR shell R plus 1. This requires R L plus 1 time per query. In the worst case, where the subarray length equals n for all queries, processing m queries would take m*n time. the space complexity would be O(m) to store the results. In contrast, the optimized approach uses the pre-computed prefix _XOR array to resolve each query in O(1) time. By doing so, the total time complexity is reduced to O(n plus m), a significant improvement for large inputs. While the optimized approach has a slightly higher space complexity of O(n plus m), due to the prefix XOR array, this trade-off is justified by the substantial gains in query processing speed. Finally, let's mathematically confirm the big O analysis. For the prefix XOR construction, the algorithm iterates through the input array n times, with each iteration performing one XOR operation. This results in a time complexity of O(n). For query processing, each of the m queries involves two XOR operations, making the time complexity per query O(1). Multiplying this by the m queries, the total time complexity for this step is O(m). When we combine these two steps, the overall time complexity of the solution is O(n plus m). In terms of space usage, the prefix _XOR array requires O(n) space, while the result array for storing query outputs requires O(m) space. Adding these together gives a total space complexity of O(n plus m). This analysis demonstrates the efficiency of the optimized solution, particularly when compared to the naive approach, as it scales well for large inputs both in time and space. When solving XOR problems, there are several common mistakes to be aware of. First, one of the most frequent errors is misinterpreting XOR properties. Unlike addition or multiplication, XOR has unique characteristics, such as a(a) equals 0 and a(0) equals a. Misunderstanding these can lead to flawed logic in your solution. Another mistake is relying on an inefficient brute force approach, where you calculate the XOR for each query by iterating through the subarray. This results in a time complexity of O(q*n), which is impractical for large inputs. Additionally, errors in constructing the prefix XOR array are common, such as forgetting to initialize prefix 0 equals 0 or making mistakes in how cumulative XOR values are updated. These errors can cascade into incorrect results. Lastly, out-of-bounds errors, like accessing prefix L1 when L equals 0, can cause runtime issues. Since prefix arrays are zero-indexed, careful handling of indices is critical to avoid invalid access. Another pitfall is failing to address edge cases. For example, scenarios like empty queries, single-element arrays, or very large input sizes require careful consideration. Missing these cases can lead to undefined behavior or incorrect outputs. Now, when tackling XOR-related problems, a key insight is to utilize the prefix XOR technique. This allows you to compute the XOR of any subarray, L, R, as prefix, R plus 1, prefix, L, assuming the prefix array is properly initialized with prefix, 0, equals 0. This reduces the query time complexity to O(n plus q). Recognizing patterns in XOR problems is also important. For instance, XOR properties like reversibility, a(b to the power of b equals a), and the identity element, a(0 equals a), are fundamental tools to manipulate and simplify solutions. To optimize your solution, always analyze the problem constraints. If the number of queries is significantly larger than the array size, pre-processing with the prefix XOR is essential. Additionally, in interviews, you should be prepared to explain trade-offs, such as why prefix XOR is more efficient than brute force, by emphasizing how it avoids redundant calculations. Lastly, variations of this problem may involve 2D arrays or modifications like toggling values in the array. Understanding how to adapt the prefix XOR method to these extensions is a valuable skill. XOR problems are often connected to other challenges, making it helpful to explore related problems. For instance, problem number 1310, XOR queries of a subarray, is directly related and uses the same prefix XOR approach. Another example is problem number 1486, XOR operation in an array, which involves straightforward XOR computation over a generated array and tests your understanding of basic XOR operations. Problem number 1442, count triplets that conform two arrays of equal XOR, takes it a step further by requiring you to count valid subarrays using XOR properties. Finally, problem number 136, single number, is a classic XOR problem that demonstrates how XOR can isolate unique elements efficiently. Reviewing these related problems can deepen your understanding of XOR techniques and their applications. When considering alternative approaches to solving XOR queries, the brute force method is a straightforward option. Here, you calculate the XOR for each query by iterating through the subarray. While simple to implement, this approach has a time complexity of O(q*n), making it impractical for large input sizes. A more efficient solution is the prefix XOR approach. By pre-computing a prefix XOR array, where prefix I stores the XOR of all elements from the start of the array to index I1, you can calculate the result for each query in constant time using prefix r+1 prefix L. This reduces the overall complexity to O(n+q), though it does require extra space for the prefix array. An even more advanced technique is the sparse table, which is suitable for static arrays. Here, you pre-compute XOR values for all ranges, allowing for constant-time queries. However, the pre-processing step has a time complexity of O(n*log n), which can be expensive. Each of these methods has its trade-offs, so selecting the most appropriate approach depends on the problem constraints and requirements. Great job following along. To summarize, we solved the problem using prefix XOR for efficient range queries. It's a useful technique, and understanding XOR properties is key. If you enjoyed this session, please like, subscribe, and share this video. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!